Okay, so from where we left off just now, right, we're still talking about paper chromatography. Now, sometimes when we do paper chromatography or even we do TLC, the components that are separated, okay, can be seen, but sometimes they cannot be seen. Like, for example, let's say in this image here, there is a separation that has taken place, but we cannot see this. So under these circumstances where you cannot see the sample or what the separation that has taken place, there are 2 or 3 ways that we can do this. One of the ways is we can first try to observe this under UV light. So when you observe under UV light, you may be able to see the spots. So the moment you see the spots, what you do is you circle them so that you know where they are. Okay, so you can circle them so that you know where they are. So like in this picture here, you can see that B contains A and then it also contains C. It has both of it. So this is one way of doing this. And in this case, what we do is everything is we use pencil. So we circle. Later on, when we're using a TLC plate, what you can do is, because it's a TLC plate, remember TLC plate is you take a silica and paste it over a backing, right? Either aluminum backing or glass backing. So what you can do is you can take a spatula and you can scrape this part out, scrape it out, put it into a test tube, put a suitable solvent and you can dissolve it, then you can filter. So you can remove the silica together with the sample. That's something that you can do. Another way of doing this is what you do is you spray it with certain chemicals. Like in this case, the chemical they're using is Ninhydrin. Ninhydrin contains nitrogen groups. So what happens is they will bond with your compounds, the compounds that you have separated. That means they make chemical bonds with those compounds and then they illuminate. That means they form a color. So like in this image, you see earlier you saw nothing. After spraying it, wow, you see so many spots. So you know where they are. The problem with this method is after you spray ninhydrin or any other chemical, like potassium manganate and so on, you cannot do the same thing. You cannot scrape this out and you cannot do further testing. You can't do that because the chemical is already contaminated. Okay, it's already contaminated. So what you will have to do is you will have to calculate the RF values for each one of the spots that you see. So you calculate the RF value here, calculate the RF value, and you repeat the experiment under the exact same conditions. So let's say you repeated the experiment under the exact same conditions. So if you calculated the RF value, you can predict that your sample is going to be somewhere here. The purple one is going to be somewhere here. You can predict based on the RF values that you have calculated, you see. So then when you repeat the experiment, you don't have to spray anything and you hope that your sample is where these spots are. So you can later scrape this out. Okay, you can scrap this region out and then put it into a test tube and do further testing. Okay, so this is one way of doing this. Then I want to talk to you about column chromatography. Okay, let's talk about column chromatography. Now, what is column chromatography? In column chromatography, the setup is something like this. We use a column. Okay, a column looks like a burette. It looks like a burette. And what we do is we fill it up with our stationary phase. The common stationary phase we always use is silica. And as you have seen this image here just now, silica, okay, silica, on the surface of the silica, there is all these OH groups sticking out. So silica is a polar substance. So what we do is we take silica powder, it's usually in the form of a powder, and then we dissolve it in the solvent. Let's say the solvent is water or the solvent is methanol or ethanol, whatever solvent that we're going to use. So back to this again. So what we do is we pour silica, in this example here, we pour silica into this column here. All right, we pour silica into this column here. So now this entire column is filled with silica. So then we have our sample. All right, we have our sample. Let's say our sample is A and then B and then C. So what we will do is this sample is also in the same solvent. That means the solvent which was used to dissolve the silica is the same solvent where our sample is. Okay, we shouldn't be having two different solvents. So then once everything is set up, you see there's a tab at the bottom here. What we will do is we'll introduce the sample to the top, at the top here. As we introduce the sample to the top, the sample will settle here at the bottom here, at the top here, right? What our job is to make sure that we keep adding more and more solvent so that this whole thing, this whole gel system here, this whole stationary phase does not dry up. So solvent must continuously be added, okay, continuously be added. So as you keep adding more and more solvent, what's happening is the components A and the components B and the components C will start coming down. If you remember the first video I shared with you, it's similar. So the components will start coming down. Now, depending on their interaction with the mobile phase and the stationary phase, they will be separated. So sometimes you can see this entire thing has a band, okay? I repeat, so sometimes you can see this like a band. You will see like a little band. Okay, so when I say band, is B-A-N-D. You see a band. And then you might see another band over here, or then you might see another band over here. Okay? And sometimes you can't see anything. When you cannot see anything, what you can do is you can turn off the lights in the lab and use a UV lamp to observe this. Okay? To observe this using a UV lamp. Then you may be able to see this. So let's say 3 bands form, okay? Let's say 3 bands form, and we have identified that the 3 bands, this is A, let's say this is C, this is B. So A is obviously going to come out of the system first. So what we say is, we say A has stronger affinity to the mobile phase. Okay, stronger affinity to the mobile phase. That's what we say, because it exits first. We say A has a lower retention time. So now you've been introduced to a word here called retention time. Earlier, when we used paper chromatography and thin layer chromatography, we talked about retention factor. Now we use retention time. So lower retention time, that means it comes from the word retain. So how long something is kept inside. So this A has a lower retention time. It takes a shorter time to come out from the column. So it comes out very quickly and is done. Meanwhile, B has a higher retention time. Okay, retention time is higher. Okay. Now, if we repeated the same experiment using a paper, let's say we use paper, right? If we use paper, and we use the same solvent system, everything exactly the same, what will happen is A would be somewhere at the top here, C will be somewhere here, and B will be somewhere here. So in paper chromatography, exactly the same thing, using the same solvent system, everything exactly the same, we will say A has a RF value which is higher. Okay, so if in paper RF value is high, in column RT is low. You see, this is for component A. If for component A, the retention time is lower in column, but RF is high. That means it travels much further away. Okay, so for component B, we say, what do we say? We say the retention time is low. Retention time is high. It takes a very long time for it to come down, but the RF is low. That means it's very close to the origin. Okay, so that's the relationship between paper chromatography, TLC, and column chromatography. In the next 2 videos, what we'll do is we will talk about this high performance liquid chromatography and gas chromatography. Now, okay, so these are separation techniques which are used to separate more complex mixtures in the lab. All right, so we'll stop here.